Hello everyone, welcome to this tutorial focus on real-time hyperspectral imaging. Well, first of all, let me introduce myself. My name is Sebastian Lopez. I'm an associate professor at the University of Las Palmas de Gran Canaria. In particular, I am part of the Research Institute for Applied Microelectronics, and here at the end of the slide you have some of my personal data in case of you want to contact me for further questions about this presentation. Well, before starting, let me say that this tutorial has been developed free of charge, only for educational purposes and without any commercial interest. All the images and figures of this tutorial have been reproduced from open sources and are sitting accordingly here, unless they were created by myself. In any case, if they may be infringing any copyright, please let me know to remove it in the next release. So here is the outline of this tutorial. Before going on, let me remind you that it is very important in order to have a good following of this tutorial that you have previously made a tutorial by Professor Antonio Plaza related with hyperspectral imaging in general. So having said this, the outline is as follows. First, I will introduce some real examples about why it is important real-time hyperspectral imaging for which applications. In particular, I will introduce one example that it is an example from a remote sensing scenario, and other one which is not related with remote sensing, but I believe that it is important also in order to understand why we need real-time performance. Then I will introduce some general concepts about parallel processing, and in particular I will focus on two different scenarios for parallel processor which are relevant here, which are onboard parallel processing as well as reconfigurable parallel processing. Then I will introduce some basics about field programmable gate arrays, FPGAs, which have become very important in this area. And then finally I will present an example about linear mixing, which is, as you may know, one of the most important algorithms or processes that we normally make with hyperspectral images. And in particular, we introduce one design that we have made in our research group, which is based on an FPGA. Well, I guess that all of you know that in a remote sensing scenario, we have a situation more or less similar to the one depicted here in this slide, where, as you can see, we have normally a satellite or even an airplane with a sensor that is able to capture some data. This data is, in the case of having an image sensor, has a structure of an image, where you can see here the data order as a two-dimensional matrix. Then this image is normally processed, and after this processing we get some information that it is very useful for different applications. You can see here some examples like geology, hydrology, agriculture, and also this information is used for the interpretation and future plans of the missions. Well, in case we have optical remote sensors, one way of classifying the images that we get is in terms of the spectral information that they carry with. And in this sense, what we know is that in hyperspectral sensors, the spectral resolution is much more detailed than in multispectral sensors. So we can see this concept here in this slide, whereas you can see here it is the multispectral data collected by a multispectral sensor, particularly on Landsat, whereas you can see we are only getting 6 points, six wavelengths. And on the contrary, if we take the same image with the hyperspectral sensors, we get much more information. which is signaled with these dots here. And as you can see, in some parts of the spectrum, this information is almost continuous. So this gives us the possibility of a better modeling the spectral response in the wavelet range. But however, we have to notice that this increase of the spectral resolution also usually comes at the expense of a spatial resolution. So normally in multispectral images we have a higher spatial resolution than in hyperspectral images, but on the contrary, in hyperspectral images we have a much higher spectral resolution. Well, in any case, although we have a reduced spatial resolution, what we have to notice is that hyperspectral data implies a lot of data to process, which means that we have very important requirements from a computational and storage point of view. Well, you can see here in this slide on the left a classification that normally is being made regarding the number of bands that you have in your image. So we can go from panchromatic to ultraspectral images. Panchromatic means only one band. Then we have multispectral, which is typically images are composed of tens of bands. Then we have hyperspectral, which is normally we are referring hyperspectral images to that images that have hundreds of bands. And then ultraspectral if we go above 1000 bands. So with this spectral information, and in particular with the typical amount of spectral information that you have in a hyperspectral image, we can make a lot of things. Some of them have been extensively covered by Professor Plaza in his tutorial, like spectral mixture analysis and also classification. But some other processes are important, like for example detection or identification, discrimination, or characterization. In any case, what it is important to notice is that the high dimension nature of these hyperspectral datasets, together with the, I would say, extremely high complexity of the processing algorithms that we have right now in the state of the art, really calls for advanced processes technique for accelerating hyperspectral related computations, especially if we are dealing, like the two examples that we are going to see later on, if we are dealing with applications that require real-time performance. So here are the two examples that I promised at the beginning of the presentation. The first one is a remote sensing example, and it is related with the images that were taken the days after the terrorist attack on the September 11 on the World Trade Center. And in particular, in this case, all these images were processed very fast in order to measure not only the fire temperature but also asbestos contamination and debris spread. So they were able to obtain maps like this with the debris composition and also charts like this with the fire temperatures. And all of this was done with images taken with the Aviris sensor on an airplane. This is a sensor from the Jet Propulsion Laboratory that give us hyperspectral sensors with 224 spectral bands. So the other example, which is in fact not related to remote sensing, but I believe it is important for the scope of this tutorial, which is understanding why we need solutions that are able to process in real-time hyperspectral images, is a medical example, and in particular it is an example taken from the European research project in which my research group is involved, which is the Helicoid project, in which our idea, our goal is to help neurosurgeons during surgery time to distinguish better in an operation which parts of the brain, I mean which tissues are healthy and which tissues are not, and they are affected normally by tumors. So what we are doing here in this project is during the surgery is taking images. We will see later on the characteristics of these images, Once we have these images, of course, we have the spectral response of all the pixels that have been captured. Then we process all these images with some algorithms, some of them very complex, some of them not. And these algorithms, because of the complexity of most of them, and also because the surgeons need to know the result as fast as possible, are processed using a high-performance computed platform. So at the end, what we are able to offer the surgeons is a superimposed image in which we are offering them the results of our classification algorithms. And in fact, what we are giving them in real time is a classification between, as I said before, that distinguish between the healthy tissue and not healthy tissue, and because of this fact, tissue affected by a tumor. So you can have here a better idea of about this project. At the left part of the slide, what we can see, at the left part of the slide, what we can see is the two cameras that in fact we are using. We are using a hyperspectral camera that is covering the visible and near infrared range, and also the other spectral camera is covering the near infrared range, more or less from 900 to 1700 nanometers. With these two cameras, we fuse the information and we get one image, and we can do some pre-processing on this image, and then after that, we with the help of this subsystem platform, we are able to process all this information very fast. And finally, thanks to this display port and this visualization software, we are able to provide within a user interface all the results to the neurosurgeons in order to take them the best possible choice. So here you have some real photos about our acquisition system. And what we have here, all the personal computer in order to control everything. But what we have here is a light source, and then you will see much better here one camera here and the other one right here. Okay, so and this is our camera. In fact, here is the light source taking images during the surgery. So here you can see an example of the one image captured by our near infrared camera, and some bands that have been plotted here. And as you can see here on this graph, you can see that we have plotted the spectral response captured by this camera by pixels that we know that are healthy and pixels that we know that are non-healthy. We in particular are plotting the average, the maximum, and the minimum. But what we can conclude from here is that in this spectral range there are almost no differences between the healthy and non-healthy tissue. But in any case, if we go to the visible and near infrared range, VNIR, what we can see is that if we plot again these spectral responses, we can see that in this part of the wavelength we have strong differences between the healthy and unhealthy tissue, and these are the differences that are in fact helping us to distinguish between these two cases. Well, here you can see all the algorithms that we are considering within this project. We have the acquisition algorithms, then we have some pre-processing algorithms, and then the classification step, which is based on spectral and mixing, in fact. And here are some results being colored in green. One of the results of the classification, and in red the other possible result. And these markers here are markers that have been allocated by the surgeons because they are our ground truth, in the sense that they know that within these they know exactly what they have, if this is healthy or non-healthy tissue. Well, in any case, these two examples, the remote sensing within the World Trade Center and the medical example, what they will, I mean, what I would like to reflect within these two examples is that we really need some methods, some platforms in order to process all these images very fast for applications that require real-time performance. And this is what I am going to review within this tutorial, the solutions that we have, and once we have demonstrated that this is very important for some applications. Well, in order to accelerate the processing of hyperspectral images, we normally go for a parallel processing solution. So these couple of slides are here in order to give an overview about what parallel processing is. So as you may know, traditionally software codes are written for serial computation. This means that they are going to be run on a single computer that has a central processing unit, the CPU. So here what we have is that the problem is typically broken into a discrete series of instructions, and these instructions are executed one after another. So what we have here is at the end that only one instruction may be executed at any moment in time. So on the contrary, parallel computing is by definition the simultaneous use of multiple compute resources. So what we have is that a situation where we are going to run our problem onto multiple CPUs. So a problem is broken into discrete parts, and then each part is broken down to instructions. So as you can see here, this is our problem, which is divided in this example into 4 parts that are going to be run on 4 CPUs. So we are getting here a theoretical speed up against the serial case of 4. Well, I don't know if you have noticed about that, but in fact the real world is massively parallel. So there are a lot of processes that happen in our real world that happen in parallel. Like for example, some of them you can see here: galaxy formation, planetary movement, weather and ocean patterns, and many others. So this is not something that only happens on the computer science side, but also in the real world we have a lot of examples. Well, in addition to that, let me notice that parallel computing has been traditionally used to model very difficult scientific and engineering problems that we can find in the real world. There are a list here of some examples related with the earth science, physics, bioscience, biotechnology, computer science, mathematics, and many others. But this is just for you to notice that parallel processing is in fact being used in a lot of disciplines, in a lot of scientific different problems. Well, the advantages of parallel processing over serial computation is we can summarize it like it is shown here in the slide. First of all, we have a save of time and or money, because in theory if you throw more resources at the task will shorten its time to completion and you will have potential cost savings, because in fact right now what we have is the parallel clusters can be built right now, as I said, from very cheap components. Of course you can solve larger problems. We need to notice that many problems nowadays are so large or so complex that it is even impractical or impossible to solve them on a single computer, mainly because of the limited computer memory. So this is the other advantage. So third advantage is that of course with parallel processing we are providing concurrency, in the sense that multiple computing resources can be doing many things simultaneously. Also, one of the advantages, very important right now, is that it enables the use of non-local resources. So it enables the use of using computing resources in networks that are connected in networks. Like for example, in this project here that I have set as an example, that I have taken as an example, which uses in fact more than or around 330,000 computers in order to solve bigger problems. So that gives us a compute power of 528 teraflops. And what is maybe the most important reason for this tutorial is that the use of parallel processing give us the possibility to cope with real-time requirements, and this is of course a must for applications under very strict real-time constraints. Well, in order to do parallel processing with hyperspectral data, we have two main approaches. The first of all is that we do a partitioning in the spectral domain, in the sense that a single pixel vector may be stored into different processing units. So each processing unit makes the computations related with only these bands, only these wavelengths, and then they communicate in order to give us the result of much more complex computations, like the spectral angle, for example. And then we have also the spatial domain partitioning, in which here every pixel vector, all the bands are stored in the same processing unit. So what we have here is a situation in which each processing unit is processing one or more than one pixels, but all the pixels that are stored there are stored with all their bands, all the spectral information. This is in fact this second approach is in fact the one that is typically used in hyperspectral imaging, because in these kind of algorithms, as Professor Plaza has explained in his tutorial, are mainly related with spectral processing, like for example the spectral angle or all the spectral and missing algorithms, and they normally do not take into account spatial information. So this is why this second approach is the most commonly used in this area. So here is a situation in which the original image is partitioning in two. You can use any of these two approaches, although as I said before, the second one is the most commonly used. And then each processing node within this data is able to obtain local results, and then at the end they communicate in order to compute the final result. So in order to do things in parallel, not only for hyperspectral imaging but for any other problem, we normally use high-performance computing platforms, because this high-performance computing platform allows us to do things in parallel. And for the remote sensing case, I would say that we have three main options. First option are clusters, which are very appealing for information extraction from images that are transmitted to the Earth, although they have different disadvantages. First of all is that they are of course not easily adaptable to onboard processing scenarios, because they have a considerable size and a considerable weight. Second, they are not radiation tolerant, and also they normally require a high power consumption. Normally in this kind of solutions we also may need a very large number of nodes in order to obtain a response in real time, and also they have high maintenance costs. So if we go for a solution that it is more suitable for a remote sensing scenario, then we have GPUs, graphics processing units, that have become very, very popular nowadays because of the video gaming industry, although nowadays are using in lots of different things radically different from video gaming. They are a very good solution in terms of cost effectiveness. They have also low weight, but one thing that is important for us to notice in this tutorial is that they require a very high power consumption, and also they are not radiation hardened solutions. So these last two issues prevent their use onto satellites, because in satellites power and radiation tolerant issues are very important, of course. So then we have a third possibility, which are FPAs, field programmable gate arrays. We will talk a little bit more about them in the next slides. But one thing that I would like you to notice is that they are very appealing for onboard processing, especially in satellites, because they have a very low weight, low power consumption, and also they can be fabricated in order to be radiation tolerant. In addition, they can be reconfigurable. We'll talk about this later on, which means that we can map an algorithm onto an FPA and then change this algorithm to run in the FPA another one, which is also very important for onboard scenarios. However, we will need to notice that if we require a response in real time, if we need FPAs to process hyperspectral images in real time, we normally need to occupy most or even all the resources within the FPA. So maybe you're asking yourself right now, which is the best solution for you for a particular case. So I would say that the first question that you will need to answer is that if you need onboard processing. If you don't need onboard processing, you can go definitely to standard solutions, like the one focused or composed by clusters, multi-cores, GPU clusters, and some others. If you do need an onboard processing solution, then maybe you will have to ask yourself a second question, which is energy an issue for me in my application? If not, for sure, one of the best solutions right now are GPUs. They are very cheap. They are also very powerful. So maybe for an airborne solution, it is one of the best options that we have right now. But if energy is an issue for you, then maybe what you have to ask yourself again is that is a programmability an issue? If not, which means that you are an expert programming, you can go to an FPA solution, which are harder to program than a GPU. But if programmability is an issue, then you may observe to implement your system by using a low consumption GPUs, which are nowadays becoming very popular, and they are in fact in most of the tablets and smartphones in the market. But of course, then you will have to notice if you have to observe also radiation issues. If you have to observe radiation issues, the only solution that we have right now are FPAs and ASICs. So, but if not, then as I said before, low power consumption GPUs can be a very good option for you. So at the end, I would like you to notice that a threat and an opportunity that we have within this scenario. The threat is that we have to balance between, I would say, three factors: programmability, power consumption, and radiation tolerance, in order to be able to pick up the best computing platform for our application. But we have here also an opportunity, a very important opportunity, is that the specialized hardware evolves very quickly and the cost is dramatically decreasing. So all of us are able to access to any of these solutions without requiring a very high budget, a very high economic budget. So once we have made an overview about parallel processing and about the different options that we have for processing in parallel a hyperspectral image, I would like to focus on a very particular case which is very important in remote sensing, which is onboard parallel processing. And this is summarized in this slide, where at the left we can see a solution with where we are not considering an onboard parallel processing. So basically this means that from the satellite or from our remote sensing system, we have to transmit to the Earth the entire image, which is a lot of information, and then we have to process the entire image on the Earth. So this may be a problem because the bandwidth that we have from the satellite to the Earth is not that high. So we may need a lot of time to transmit the image, and also a lot of time to process the entire image on the Earth. So of course this is not a good solution for those applications requiring real-time performance in which we have to process the images very quickly. So let us consider a solution with onboard parallel processing, which is summarized on the right part of this slide, where in this onboard system we are able to do on the satellite compression of the information and or processing of this information. So what we are achieving here with this solution is that we only transmit or a compressed version of the data, or even just the results to the Earth, or the results of having processed the image. Let's think about a spectral emitting case in which, for example, we can transmit the abundances and the end members to the Earth station. So at the Earth station, we only need to decompress the data and process the data in case of it is not processed, or maybe we can handle with a situation in which we have to do absolutely nothing because we have received the results. So of course this situation is this kind of a scenario is smarter than the first one, in the sense that we need to transmit only a few amount of data, and this can be transmitted very quickly. So this is of course a situation that it is very good for applications in which we require real-time response. So as I said, the problem that onboard parallel processing tackles with is that in many applications we need real-time requirements, but what we have is large data volumes. So we need a lot of time to process this data, and a lot of time also to in the Earth, but a lot of time also to transmit the data to the Earth. So if we go for solutions with automatic onboard processing, of course we are getting first a reduction of the cost and the complexity of the ground segment of the mission. It also enables to take autonomous decisions to be taken on board. So that means that we are getting faster critical decisions. And of course, as we have said before, this means that we are obtaining a huge reduction of the communication bandwidth, and also we are doing simpler and faster computations. So of course this has potential for a lot of applications in Earth observation missions, in planetary exploration missions, or even in military applications, and I would say in all the applications that require real-time performance. So here is a graph where we summarize some satellites with hyperspectral imaging instruments that of course can benefit for these onboard processing systems. Here we have the satellites with the hyperspectral imaging instruments they are carrying with, expressed in terms of the number of bands and the spatial resolution of the images. And also we have some other solutions, some other satellites, that are outside this graph. And here what we can see in red are satellites that are supposed to be launched in the near future. And what I would like to express here is that all these satellites that carry hyperspectral imaging instruments of course can benefit from this onboard parallel processing that we will see after on. How can we do that? So one other thing that I would like to focus on this tutorial is about not only onboard parallel processing but also onboard reconfigurable parallel processing. So as we have seen before, hyperspectral image processing applications can greatly benefit from having onboard processing modules. But what we have to notice is that normally in satellites we are in a situation and we would like to run different algorithms because we are dealing with different applications. So for example, let's think that we have a situation in we would like to compress the data, but in some other situations to perform a classification over the data we have captured, or a mixing or target detection. So how I say this, it is of course very appealing to have the possibility to have a dynamically reconfigurable hardware on board, which means that within the same piece of hardware we can put an algorithm or another according to the preferences of the applications that we are targeting. So for doing that we have reconfigurable computing that give us a high performance in the sense that we have a high processing power, and as I said before, we can reconfigure what we are doing so we can switch from one algorithm to another. So this is right now no longer a promise but a reality, and as I said before, it is very feasible right now to have several algorithms implemented onto the same board, and we just select the one in which I'm interested at any moment. So of course this is very attractive for satellites, but of course although this technology is mature right now, we have still some technological challenges that still remain open. So a typical classification of reconfiguration is the one that it is exposed in this slide, which takes into account two factors. First, the area that it is affected, and second, the relation with application. So about the area, it means full or partial if we are fully reconfiguring our hardware device, or we are only reconfiguring one part of our hardware device. This is the difference between full and partial. And also the relation with application means static and dynamic if we are stopping the FPGA in order to reconfigure it, or we allow that a part is running and the part that we are reconfiguring is the one that is stopped and being reprogrammed. So we have different options for reconfiguration. For example, we have first a scenario when we have a full reconfiguration and a static reconfiguration, which means that we are reconfiguring all the FPGA, which means that we have a high reconfiguration overhead and the design is interrupted during reconfiguration. Then another scenario is partial reconfiguration, static partial reconfiguration, which means that we are only going to have reconfiguration on one part of the FPGA. This is why we have a reduced reconfiguration overhead, but we have to interrupt the full operation of the device. So the smartest one is the dynamic partial reconfiguration, in which the design is not interrupted, and while this is not interrupted, we are reconfiguring other parts of the device. So again, we have a reduced reconfiguration overhead, and as I said before, the smartest possible situation. Well, as I announced before, we have still many challenges here. One of them is, of course, how reconfiguration is being affected by radiation, or in other words, how what would happen if an error caused by radiation affect our device during reconfiguration. Also, one of the challenges is the extra power that we need for reconfiguration, which is all the power issues are critical in satellites. And then that it is a technology that is relatively new in remote sensing, which means that we have a learning curve that we have to observe, and also is the fear of change that always happens with new technologies. In addition, we have to notice that only few techniques have been developed taking into account reconfiguration for hyperspectral imaging, because I would say that this technology is much more mature for other fields, like for example multimedia and video compression. And as I said before, this is related with the first thing that I mentioned. We have to notice that one of the challenges is that the reconfigurability can generate uncontrolled situations in aerospace, which is always not good. So we need to further advance within this topic, although it is very promising. And it is not me only saying, the one that I'm only saying that it is very promising. So we have a look about onboard, what space agency thinks about onboard parallel processing. We can see, for example, the opinion of the European Space Agency, the ESA, where, as you can see, they are saying that data rates and data volumes produced by payloads continue to increase, while the available downlink bandwidth to ground stations is comparatively stable. So this results in challenging requirements, I will say that in very challenging requirements, in fact, for future onboard payload data processing systems, which unfortunately cannot be met with space-qualified processors available today. So ESA concludes saying that many new missions and applications in the areas of science and exploration, Earth observation and telecom will require new and more powerful onboard processing platforms. So I think that the message is very clear. Onboard processing platforms is no longer a promise, it's a reality. It has a lot of challenges open, but it is something that we have to definitely go further, because it has a lot of benefits for remote sensing, and in particular for satellites. Well, if we come to the particular case of applying onboard parallel processing for hyperspectral images, I would say that we have two main possibilities, as I mentioned before. One of them is compression, that could be lossless or lossy, in the sense that if we are introducing losses in the compression procedure. But in any case, lossless or lossy, they are mainly based on the same idea, which is exploiting the interband and intraband correlation in order to reduce the data transmitter process. I mean, this is the idea of exploiting the idea that each pixel in the regarding its spatial neighbors should be very similar to these spatial neighbors, and also the wavelengths, if they are captured in a hyperspectral sensor, where the difference between consecutive wavelengths is not that high, the values of one pixel when we go from one wavelength to another should be also not that different. So the second branch, the second possibility, is about processing these images, and in this case I have selected three processes that can greatly benefit from onboard parallel processing: target detection, which is typically for military applications, and also classification and mixing that have been covered by Professor Plaza in his tutorial. In fact, what I am going to do in this tutorial is to show you an example about how we can use FPGAs for mixing. So before that, I would like you to notice, or you to know, in case you don't know about them yet. some general things about FPGAs and the differences with ASICs, with application-specific integrated circuits. So in the case of the first ones, ASICs, when we have a design and we are going to implement this into an integrated circuit, this is an expensive and time-consuming fabrication process in a semiconductor foundry. And although at the end what we get is a very good circuit, a very specialized circuit that makes the process for what it was conceived in a very good manner, in the sense that can process all the data very fast with low power dissipation. But the main drawback is that with this ASIC we can only do one thing, while with FPGAs, with our basically programmable hardware, when we do, what we can do is to reprogram the hardware every time that we want and to run different algorithms onto the same piece of hardware. So of course we are not going to get the same performance levels of ASICs, but right now with modern FPGAs we get, I would say, close levels of performance, and we have of course the advantage of the reprogramming. So the basic structure of FPGAs is the one shown in this slide, where what we have is a two-dimensional matrix of what we call CLBs, configurable logic blocks, that are connected through a programmable interconnection network. So basically in these CLBs, what we can do is very simple operations with the structure that is inside the CLB. But we have a lot of CLBs on an FPGA. So if we map these simple operations into a lot of computing resources and then we interconnect them properly, what we can do at the end is a complex operation by using these simple structures. Additionally, what we have in these FPGAs are input and output blocks, and they are shown here, in order to exchange data with the outside world. And also in some FPGAs, especially in the modern ones, what we have normally is embedded complex functional blocks, like for example on-chip memory, blocks that have been especially designed for digital signal processing computations. Like for example, what we have normally there are very specialized multipliers, general purpose processors that we can implement, also transceivers and so on. So how do we map an algorithm into an FPGA? Well, this is normally a complex procedure that involves several different steps and normally also different software environments. So it all begins with a specification. Then we have to translate this specification into a hardware description language, where the most common options are VHDL or Verilog. These are languages in which we can express which things are happening in parallel and which things are happening in a serial fashion. With this code we can perform, by utilizing different software tools, a functional simulation, which means a simulation in order to know if the code is doing what it is supposed to do according to the specifications. Then if the code is functionally correct, what we have is typically the synthesis process, also helped by a software tool in which we translate our code into a set of logic gates, and then we can perform a post-synthesis simulation in order to know if everything is still going well. Then we have the placement and routing, or the implementation, in which we map these operations that have been expressed in terms of logic gates according to the computing resources that we have into the FPGA. And then, of course, we have at the end of this process, we can perform a simulation in order to know if everything is still going well. And then we have finally the configuration into the FPA and the on-chip testing. Well, as I said before, I am going to introduce in this tutorial an example of the use of FPAs for performing in real-time linear mixing. And as you know from the previous tutorial, the goal of mixing is to find a set of pure spectral components, normally known as end members or pure pixels, that can be used to mix all the other pixels in the data, the pixels that are non-pure. So at the end, what we are trying to find is the fractional coverage, also known as abundance, of each member in each pixel of the sim, which in fact can be approached as a geometrical problem. And as you can see here, what we have is a set of data plotted in two bands, and at the end what we try to do with the end member extraction step is to find E1, E2, E3 that allow us to express any other pixel in the image as a linear combination of these three pixels. So in this perfect situation that we have here, we don't need no other term, but as you know, images are normally noisy, and this perfect situation cannot be in all the cases achieved. So in order to fully model each pixels, we may need to add an additional terms that in fact it is related with the noise of the image. So one of the most famous algorithms within end member extraction is the VCA, the Vertex Components Analysis, which was uncovered by José Nascimento and José Viurques Dias. And this algorithm is based on the concept on orthogonal projections, and the main idea is that at the end we start with a random vector, and then we project the whole image into a direction orthogonal to this first vector E0, and we get the pixel that has the maximum projection onto the direction signaled by this orthogonal vector F1. So this pixel becomes our first member, and then we repeat the process in the sense that we get a vector that is orthogonal to this member E1, and then we project the image again onto the direction signaled by this new vector, and then we get the pixel with the maximum projection onto this direction, which give us the second end member, and we continue with the process in the sense that we always do the same. We always get a vector that is orthogonal to the end members that we have found so far, and then we project the image into the direction of this orthogonal vector, and we get the pixel that gives us the maximum value within this projection. So this new pixel is selected as a new end member, and this is repeated p times, where p is the number of members. So here at the right you have the pseudocode. So for this algorithm, as I said, we do for p times to get an orthonormal vector, which is orthogonal to the all the members found so far, and then we project the whole image, the whole hyperspectral image into the direction signaled by this vector, and we select the pixel which has the pixel of the image that has the maximum projection into this direction as the new end member. So we update our end members matrix, then we again compute a new vector until we do it p times. So at the end what we have is the set of vectors that are from E1 to EP. Well, VCA is a very good end member extraction algorithm that has been sufficiently tested, but unfortunately for us, and unfortunately for applications that require real-time performance, it has a very high computational cost. In particular, this high computational cost comes from two things. First of all is the computation of the vector f, which requires the computation of a pseudo-inverse of a matrix and then the product by a matrix of the pseudo-inverse, which being this process usually performed by a singular value decomposition. And then we have to project the whole image onto this vector, which is also, due to the dimensions of the matrices involved, a complex operation. So what we made in this research is, first of all, what we think that was the smartest strategy within this problem is try to alleviate this computational cost. And what we did is to create a new algorithm that we entitled Modified VCA, MVCA, in which the computation of the f vector is being done by another orthogonalization strategy, in particular by using the Gram-Smith algorithm, which give us a very low computational cost solution for finding an orthogonal vector in each iteration of the loop. In fact, this operation only involves very simple operations like adding some multiplications and divisions. And also the other thing was to use fixed point arithmetic in terms of floating point arithmetic for the projections, in the sense that what we need really to know is not the value of the projection itself, but where is the pixel that gives us the highest projection. So what we think is that this pixel can be found using a reduced precision operation, by using fixed point precision instead of floating point precision, because this will not change the position of the end member. Of course, when you deliver a new algorithm, you have to first to test it and to be sure that this algorithm has not only a lower computational cost, but give us in this case a similar and mixing performance than the original algorithm, the VCA. So these are some very general details about our architecture, in which, as you can see here, we here have a memory for the image, and we have here a block in charge of the image projection, which receives the f vector and multiplies this with the image, which was stored in this memory, and as a result we get the index with the pixel that give us the maximum projection in each iteration. And then we have here these two blocks that are related with the computation of the f vector, and this is being done in floating point, but the projection, because of the reasons that I mentioned before, is being done in fixed point precision. So I'm not going to get much more into the details, but just for you to notice about the complexity of these modules. As you can see here, these are the detailed structure of how we are computing everything in order to get the f vector. But what I would like you to notice is that instead of going to a singular value decomposition, we are getting here, what we are using here is very simple computing structures, and at the end we are involving only some multipliers, some others, and divisions in a very simple manner. These are the multipliers that are able to obtain the projections within the Gram-Smith orthogonalization strategy. If we look to one of the other blocks, we see again more or less the same, in the sense that all the operations are mapped by using very simple computing structures, which is very good for these solutions based on FPAs. And if we go to the projection itself, what we can see is that we have here a set of multipliers in order to process in parallel each component of the vector f, each of the p components of the vector f, and each of the p components of the image. Let me remind you that in the VCA we have first a dimensionality reduction step, so we process the image in p bands, And then we have some adding stages in order to compute all the projections, and at the end a comparator in order to know which is the pixel that gives us the maximum projection value. So if we compare the results of the MBCA against the original BCA algorithm in terms of computational cost, what we can see here is that for the two most computationally complex processes of the BCA, which are the computation of the F vector and the projection of the matrix onto the F direction, what we can see is that we are getting a very huge reduction of the computational power that we need, measured in terms of the number of floating points operations that we need. And this is well summarized here in this graph. And as you can see here, we have the represented the ratio between the number of floating point operations that the BCA requires and the number of floating points operations that the MBCA requires, with respect to the number of members to be extracted, and also for different situations, for different images with different number of pixels, being R the number of pixels. So as you can see here, especially for images composed by a more or less high number of pixels, here for example 10,000, which is, I would say, a common situation for hyperspectral sensors, or even to have much more pixels, we are getting a significant advantage in terms of the computational power that we need when compared with the BCA. Of course, as I said before, you have to test this with images in order to test the mixing performance that you are getting. So we tested with synthetic images in which we know the difference, in which we know, the results in advance. And basically what we are trying to say here with this graph is that independently of the number of members and on the noise of the image, the results were more or less the same. I mean, the difference between the MBCA and the BCA were in fact negligible and noise independent. Yeah, and here are some results that we obtained for a very famous image, use a real hyperspectral image, which is cuprite, taken with the Aviris sensor. And what we plot here is that the solution, the spectral angle, with respect to different materials that were reported in the original BCA paper. And what we plot is the maximum spectral angle obtained by our solution, the maximum spectral angle obtained by the BCA, and also the minimum spectral angle obtained by both algorithms. And what this graph is trying to summarize is that both algorithms behave more or less the same, in the sense that the higher errors and the smaller errors for both cases are, as I said before, very similar. So this is another way of testing that both algorithms behave in a very similar manner. So here are some results about our implementation into the FPA, in which we did two implementations regarding the projection block, which is the block in charge of projecting the image into the direction signaled by F, being F the orthogonal vector of the to the n members found so far. And as you can see here, we are plotting the number of FPA resources, again the number of members. As you can see here, in terms of the register use and then the lookup table use within the CLBs, of course, what we get is a significant advantage if we go for the fixed point solution, in the sense that we are requiring less resources and we are getting the same results. In particular, for the case of the cuprite, which is composed by more than 45,000 pixels with 224 bands each, what we get is that the time in order to process this FPA goes from 2.8 for the fixed point precision solution to 3.6 milliseconds for the floating point precision. So we are getting not only reduction of in the number of resources required, but also in the time. and these times allow us to process this image in real time. So with this example I conclude this tutorial. I hope that you have enjoyed it, and in any case, of course, you are free to contact me in case you have further questions. Thanks a lot for your attention.